Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very important past paper question on quantum physics from October-November 2021, Paper 4, Variant 1. I said this question is very important because the concepts we will discuss in today's class, these concepts are most frequently asked in past papers. So, understanding of today's lesson is very important to understand quantum physics and to answer questions in your exam. In today's lesson, first of all, we will discuss about particulate nature of electromagnetic radiation. Or simply I can say particle nature of electromagnetic radiation. And also we will discuss the experimental phenomenon that provides evidence for particulate nature of electromagnetic radiation. Then we will talk about wave nature of matter, and also we will discuss experimental phenomenon that provides evidence for the wave nature of matter. We will also talk about de Broglie wavelength. We will also discuss how to calculate the final speed of beam of electrons when they are accelerated through a potential difference. At the end of the video, we will also talk about effective wavelength of electron. For part A, we need to state an experimental phenomenon that provides evidence for the particulate nature of electromagnetic radiation. Electromagnetic radiation, simply you can understand, light is also electromagnetic radiation. Now, light is an example of electromagnetic radiations. Particulate nature means particle nature, means light behave as a particle. So we need to state experimental phenomenon for that situation where light behave as particle. Now, if you look at this one, you can see this is the light. We shine light on metal and electrons are emitted from this metal. So how we can explain this one? This phenomenon we cannot explain if we treat light as a wave. We can only explain this phenomenon if we treat light as particle, means light consists of particles, or simply we can say light consists of photons, packets of energy, discrete quantity, packets of energy. So we can explain this phenomenon. And this phenomenon is photoelectric effect, means the emission of electrons from metal surface due to light. So that is called photoelectric effect. And this is the experimental phenomenon that proves that light behave as particle, or it shows the particulate nature of electromagnetic radiation. So for the first one, simply you can say photoelectric effect. For the second part, we also need to state an experimental phenomenon for the wave nature of matter. First of all, let's try to understand a little bit about matter. Matter means that electron. Electron is matter. You, I, all of us, we are examples of matter. But in this case, we will only focus on electron. If you look at this experimental setup, in this case, we accelerate electrons first of all, and then those accelerated electrons, they pass through graphite. And on the screen, we observe concentric circles. Means electrons, they form concentric circles on the screen. And these concentric circles we can only explain, or they can only be formed if electrons behave as wave. If electrons behave as particle, in this situation, concentric circles will not be formed. So that is evidence of wave nature of electron, or we can say wave nature of matter. And this is called electron diffraction. So simply we can say this is electron diffraction. And this is evidence of wave nature of matter. Wave nature of matter. Sometimes we call matter waves. But if you look at the gap between two consecutive circles, that is equal to lambda. Means that is the effective wavelength of electron. We can also calculate if we have the informations. So the second one is, here we can simply write down electron diffraction. This question has 2 marks. If you have written these 2 points, you will get 2 marks. So these are B marks. It must be in the answer. For part B, a particle of matter moves with momentum p. We need to state an equation that gives the effective wavelength of the particle, and we need to state the name of any other symbols used. In this case, you can see we have symbols for two quantities, for momentum and for wavelength. And if we use any other symbol for any other quantity, we have to state the name of the symbol. So first of all, let's try to write down the formula, the equation for lambda, effective wavelength. This is equal to, lambda is equal to h over p. So h is a new symbol we have used. This symbol was not given to us, so we have to state the name of this symbol. And h is simply Planck constant. So simply we can say this is Planck constant. So if you write down this one, you will get 2 marks. 1 mark is for this one. If you have written this equation, you will get 1 mark. And this is M mark actually. This is not B mark. This one is M mark. You must have written this one. So you must have written this one. If you have written this formula, you will get 1 mark. This is M mark. And the second mark is answer mark. If you have written Planck's constant, you will get the second mark. But if you couldn't get this mark, means if this formula is wrong, you will also not get the second mark. Now let's move on to next one. Is asking you state the name given to the wavelength of the moving particle, and that wavelength actually is called de Broglie wavelength, after scientist who gave the idea of wave nature of particles, de Broglie wavelength. And so the name for this one is de Broglie wavelength, because de Broglie was the first scientist who proposed that if light can behave as particle, matter can also behave as waves. And this part has only 1 mark, and this is B mark. If you have written de Broglie wavelength, you will get this mark. For part C, it is given to us electrons are accelerated from rest through a potential difference of 4.8 kilovolts. We need to show the final speed of electrons is 4.1 times 10 to 7 meters per second. This question is just based on conservation of energy. Let's try to understand this one with the help of uniform electric field. Let's say we have 2 plates. One plate is negatively charged, means the net charge on this plate is negative, and the net charge on this plate is positive. And the potential difference between these 2 plates is 4.8 kilovolt. So we can say there's a voltmeter that is connected between these 2 plates, and the reading on this voltmeter is 4.8 kilovolts. Means the potential difference between these 2 plates, that is equal to 4.8 kilovolts. And there is a uniform electric field between these 2 plates. And electric field always points from higher potential to lower potential. So this is direction of electric field lines from positive plate to negative plate. We are ignoring edge effect in this case. Actually, electric field here, it will be not uniform at edges, but we are just ignoring edge effects. Imagine that electron is placed close to this negative plate, and it is given to us, it is started from rest, means its initial speed is 0. So when electron is at this point, the energy it has, that energy is electrical potential energy. But now if we let this electron go, this electron will accelerate to the positive plate because there is attractive force acting on this electron. When this electron will reach at this point, its electrical potential energy will be converted into kinetic energy. Now simply we need to equate these 2 energies. So we can say EPE lost in this case, that will be equal to KE gained. So I can say KE gained, kinetic energy gain, and in this case we can say lost EPE. EPE lost in this case is equal to Q times delta V. Delta V is the potential difference between 2 plates, and kinetic energy gain, because it is starting from the rest, so the initial kinetic energy is 0. So simply we can say the final kinetic energy means the speed at this point. Let's say the speed is V at this point. So we can say final kinetic energy is equal to 1/2 mv square. We need to calculate V, so simply we can write down V in this case will be equal to 2Q times delta V divided by m. And if we take the root of this one, that is the final speed. In this case, value of Q This is electron. So the charge on electron is 1.6 times 10 to negative 19 coulombs. Delta V is given to us, that is 4.8 kilovolts. So we have to multiply with 1000. We have to divide by mass of electron because electrons are accelerated. So we have to divide by mass of electron. And mass of electron is 9.11 times 10 to negative 31 kg. So if we solve this one, our final answer will be 4.1 up to 2SF times 10 to 7 meters per second. This is what we have to show. So this is our final answer. This question has 2 marks. The first mark you will get if you have written this formula. C1 mark you will get. And the final mark is answer mark. If you have got the right answer, you will get second mark. For the second part, question is asking us to calculate the effective wavelength of a beam of electrons moving at the speed in C1. In C1, we have calculated speed of electrons. V was equal to 4.1 times 10 to 7 meters per second. Now we need to calculate the wavelength of electron if the electron is moving at this speed. Because we have discussed in part A, electron also behave as wave, means the wave nature of matter. So now we need to calculate the wavelength of matter, or we can say the wavelength of matter waves. So how we can calculate the wavelength of matter waves, or the wavelength of matter means the wavelength of wavelength of electrons. We have discussed that the wavelength lambda, the effective wavelength, this is equal to h over p. P is the momentum, h is the Planck's constant. So we can also write down this one h over mv, because the momentum is equal to mass time velocity. So this is our effective wavelength. Now simply we need to plug in values. Planck's constant, first of all, Planck's constant is equal to 6.63 times 10 to negative 34 joules second divided by the mass. We are talking about electrons, so we have to use mass of electron, and mass of electron is 9.11 times 10 to negative 31 kg, and we need to multiply with speed of electron, and the speed of electron is 4.1 times 10 to 7. So if we simplify this, you see in this case we have 2SF here, we have 3SF here, so this has 3SF, this one has 2SF, and this quantity has 3SF. And so in our final answer, we have to use the least number of SF. So we will be using 2SF in our final answer. So our final answer will be 1.8 times 10 to negative 11 meters. And this is the wavelength of electron if the electron is moving at this speed. But if we increase the speed of electron, meaning if we increase v, this lambda even will get shorter. That if we decrease this one, if we decrease speed, lambda will increase. So this is our final answer. This is how you can calculate. And this question has 2 marks. If you have written these steps, mean you have plugged in values of Planck's constant, mass and speed, you will get 1 mark, that is C mark. And the last mark you will get if you have done correct calculations and you have got the right answer. If you have got the right answer, you will get second mark, that is answer mark.